Good morning. This session I am going to show you some application of Lagrange's mean value theorem. Mind you, the Lagrange's mean value theorem concept once more here. That is about finding a point in an interval AB where tangent will be the interval we are taking, say AB, and the function is y equal to fx. This function is continuous here and differentiable in the interval which is open, that is AB. Then there exists a point in between A and B where the tangent drawn to the curve will be parallel to the chord AB. That we have seen in the previous session. I have given you the proof and we have done some application. Right now I am going to show you how to prove some inequalities with the help of Lagrange's mean value theorem. You just note it down here that fb minus fa by b minus a is the value of derivative. Now before giving you any problem, before discussion of any problem, just see one thing here, that fb minus fa, if we cross multiply and assuming b is greater than a, then b minus a going to be positive quantity. So fb minus fa going to be f dash c into b minus a. Now we can compare the values, functional values between 2 points a and b by using this equation. This one as an equation. Under what condition you say that fb greater than fb greater than a implies fb is greater than fa? That you have to see the right hand side. When you are saying b greater than a, it means b minus a is a positive quantity. So if b greater than a, that is b minus a is a positive quantity and f dash c also, then fb minus fa should be greater than 0, that is fb greater than fa. Okay. So just I give you one example. Suppose there is a function fx and you want to compare the value of fx with f0. Initially you assume that x be greater than 0, then fx minus f0 will be equal to f dash c is a point in between 0 and x. You are taking this interval 0 to x. In this interval fx minus f0 will be f dash c multiplied by x minus 0. Now if x greater than 0 and f dash c greater than 0, then what will you get? This will imply fx minus f0 greater than 0, that is fx is greater than f0. Fx will be greater than f0. So values of the function at 0 and x can be compared by using Lagrange's mean value theorem. Most of the cases interval will be given. If interval is not given, you assume the interval in this manner and there you prove that fx will be greater than f0. So let us see how to prove some important inequalities which you have already used in some problems without giving a proper proof. How to get those proofs by using LMVT. I am taking this function that tan x is greater than x in the interval 0 to pi by 2, that we have to see, that we have to prove. If you find the similarity with this thing, comparison of fx and f0, then you all can see that tan 0 has value 0. But to prove tan x greater than x, we need to take the function in such a manner that that function will be tan x minus x and that will be greater than 0. I am simplifying the idea. To prove that in analogy with this one, I am giving you the proof. to prove that tan x greater than x, which implies that tan x minus x greater than 0, we consider the function, consider fx equal to tan x minus x in 0, x. In this interval, that obviously x is belonging to 0 to pi by 2. X is less than pi by 2. That we will keep in our mind. That x greater than 0, less than pi by 2. Okay. And throughout this interval, the tan x function is positive. X is also positive. But to prove this one greater than 0, we notice one important thing, that f0 here is tan 0 minus 0, that is equal to 0. So you can take the help of Lagrange's mean value theorem, the discussion we have already made, by taking fx as tan x minus x. So here, by using LMVT, on fx equal to tan x minus x in 0, x, we have fx minus f0 equal to, there exists a point C where this is f dash c into x. This equation I told you, we can use it wherever required. As fx and f0 are well defined, I am taking the help of this thing. C is a point in between x and 0. Let us see what happens there. That f dash c is what? You have taken fx here, that fx is tan x minus x. So f dash x is sec square x minus 1. This is positive for x less than pi by 2 and obviously greater than 0. This is a positive quantity. And x is also positive quantity because x is greater than 0 and less than pi by 2. So x is positive, f dash c also positive. So this thing going to be greater than 0. This implies fx is greater than f0. So tan x minus x greater than 0. That is tan x is greater than x. So very simple method we have followed here to prove that tan x is always greater than x in the interval 0 to pi by 2. Same manner we can prove sin x less than x. How to prove it? Sin x less than x. To prove sin x less than x, I mean the second proof, to prove sin x less than x, we are taking that fx be sin x minus x. You can take x minus sin x also. What is the value of f0 here? That is sin 0 is 0, minus 0, that is also 0. So fx minus f0 is equal to f dash c multiplied by x. This can be used where x is greater than 0. So let us see just the value of f dash x. What? Then we will decide about f dash c. F dash x, I mean derivative of fx is cos x minus 1. If you take minus common, this is 2 sin square x by 2, always less than 0. So on the right hand side part, this quantity is negative. What about this quantity? This is positive. Therefore, fx minus f0 is going to be less than 0. This implies fx less than f0, or sin x minus x less than 0. Therefore, sin x is less than x. So second one is also done just by using Lagrange's mean value theorem, very simple manner, very convenient manner. Let us see the third one, cos A minus cos B less than C. How to prove this? Can you prove it? Cos A minus cos B? Of course we can prove it. To prove that, what kind of function we are going to take, that you can guess. What function can we take and what interval can we take, that matters. Here no interval is given, just for two values of A and B. Cosine A minus cosine B less than equal to mod A minus B, that we have to prove. So we are taking the function fx equal to cos x in the interval A comma B. This is closed interval, of course. You are taking this. Now in this interval, Lagrange's mean value theorem, what form should take? It was 0 to x in the previous two sums, but here it is A to B. So f dash C, if there is a point C in between A and B, this is going to be fb minus fa by b minus A. So fb minus fa will be b minus A into f dash C. This we are going to use as an equation. So let us see what happened. What is cos B? fb here. fb is cos B. fa is going to be cos A. Therefore, f dash C, f dash x will be what? If fx is cos x, it will be minus sin x. So f dash C will be minus sin C. Now minus sin C, if we use this as an equation, this will be cos B minus cos A by B minus A. You can see what is given in the sum, that is mod of cos A minus cos B less than equal to mod of A minus B. They have asked you to prove. So we need to take mod of both sides. If we take mod of both sides, then mod of this, what is mod of minus C? It is mod sin C. And modulus of two quantities, modulus of the quotient equal to modulus of numerator minus by modulus of denominator. So cross multiply, mod cos B minus cos A will be equal to mod B minus A into mod sin C. Now what happens mod sin C? You know, mod sin C is a quantity which is less than equal to 1. So this thing going to be less than equal to mod of B minus A. So mod of cos B minus cos A less than equal to mod of B minus A. You can interchange these two quantities because mod of A minus B is mod of B minus A. So mod of cos B minus cos A going to be mod of cos A minus cos B less than equal to mod of A minus B. Both sides remain positive quantities, so interchanging their position doesn't affect the inequality. Alright. Now to prove number 4, that x by 1 plus x. So far in these three sums we have seen that only one inequality is present, the interval given or interval we have assumed to prove it. But for this one, the interval is 0 to infinity and two parts are there for the function. How to solve it? So let us start with number 4. In sum number 4, to prove this inequality, we will take part by part. We are taking this one as one part and then we are taking this as one part. So let fx equal to x by 1 plus x minus ln 1 plus x in the interval 0 to infinity, because x greater than 0 given. So f0, let us check first whether that fb minus fa going to be 0 or not. We are checking. This thing is 0 by 1 ln 1 is 0, so this part is 0. So we can use this one as an equation as I told you earlier, that fx minus f0 is equal to, this thing going to be equal to f dash c into x minus 0. Let us see what is f dash x here. If you find f dash x, it is going to be 1 plus x whole square 1 plus x minus x minus 1 by 1 plus x. So what do you get as f dash x? So f dash x is equal to 1 by 1 plus x minus 1 by, so this thing is 1 minus 1 plus x by 1 plus x whole square. So this is minus x by x plus 1 whole square. This is always a negative quantity. So f dash x is a negative quantity. That x lying in which interval? X we said it is greater than 0. And in the interval, if we take 0 to infinity, in this interval, x is a point. At any point, if you find the derivative, that c lying in the interval 0 to infinity, that, or here the interval you take 0 to x, so f dash c is minus c by 1 plus c whole square, that is also negative. So what do I find there? This quantity is negative and this quantity is positive. So what about fx minus f0? This thing is less than 0. f0 is 0 and fx is this. So x by 1 plus x minus ln 1 plus x less than 0. Therefore, x by 1 plus x by 1 plus x will be less than ln 1 plus x. Okay. So this part is done. The fourth part where we are supposed to prove the first part only done. Now to prove x greater than ln 1 plus x, we will be assuming for the second part here. This one's second part. We'll start the same manner by taking another function phi x equal to, let phi x equal to x minus ln 1 plus x. Again, this satisfies the condition of Lagrange's mean value theorem, and phi dash x, we can see that 1 minus 1 by 1 plus x, x by 1 plus x. For x greater than 0, this will be a positive quantity. And phi x, then if we use the equation that phi x minus phi 0 equal to phi dash c into x minus 0, then phi dash c is a quantity, phi dash x, you can see here x by 1 plus x, it is positive quantity, phi dash c also will be positive, and x also a positive quantity. So this will imply phi x greater than phi 0, or phi x minus phi 0 is greater than 0. Therefore, phi x greater than 0, but phi x is what? X minus ln 1 plus x. So x will be greater than ln 1 plus x. Fourth one is also proved here. We are going to prove the fifth one now. Fifth one means that this is the sum. Number 5 is this thing. We are going to prove root 1 plus x is less than 1 plus half x. How to prove this? How to prove this function? You can proceed with the method you have learned already. Otherwise, you take the function fx equal to root 1 plus x in 0x, this interval. Okay. What is f dash x? F dash x will be 1 by 2 root 1 plus x. Alright. 1 by 2 root 1 plus x. What is f0 here? f0 is root 1 plus 0, that is 1. Now you can use this one as an equation. Fx minus f0 equal to f dash x, f dash c you write better, f dash c multiplied by x minus 0. What is f dash c? It is a positive quantity. For all x greater than 0, there is no scope of getting negative quantity. And what is x minus b? No, we can't say that. So if you put the value of fx here, root 1 plus x, f0 1, then it is f dash x into x minus 0. F dash c. C is a point in the interval 0 to x by Lagrange's mean value theorem. Now f dash c we substitute and x minus 0 is x. You just check this one carefully. C is a point like x only. So if somebody says that 1 plus c is greater than 1 or root 1 plus c is greater than root 1 means 1, then 1 by root 1 plus c will be less than 1. So this thing is less than half x. So this implies root 1 plus x is less than half x plus 1. This only we are supposed to prove, that root x plus 1 is less than x by 2 plus 1. Okay.